Hi, and welcome to Calculus with soon-to-be Dr. Megan. Today we're going to be talking about Chapter 3.11 from Rogowski, which is related rates. To start off with, we're just going to talk about the concept, kind of what we mean when we say related rates. Then we'll go through the steps that we can follow to solve those problems, and finally we'll do a couple of examples. Okay, so what do we mean when we say related rates? The entire idea is that some things change at rates that are related to one another. So to give you kind of an idea of what I mean by that, let's think about a ladder that's sliding down a wall. We know that the top of it is going to be sliding down, like this, and the bottom is going to be sliding out, like this. Now, they're going to be sliding at different rates, but the rates are related to one another. And now with our tools of calculus, we can describe exactly how that happens. Okay, so we have some steps that we can follow to make these problems a little bit easier for us. The first thing that we always want to do is to draw a picture. For example, in the last one, I drew a ladder for us so that we can actually see the relationships that are going on. The next thing we want to do is to write down what we know and label the important parts. So as I mentioned, we were talking about the top of the ladder and the bottom of the ladder. So let's label them. For example, let's call the place at which the top of the ladder is, we'll call that H, and we'll call the bottom D. Now, I said that we wanted to talk about the rate at which they're moving, so we're talking about the derivative with respect to time. So this here is going to be dH dt, and down here we'll have dd dt. Good. Now, once we have that done, the next thing we want to do is write an equation that relates the variables that we're interested in. Sometimes that equation is ready made for us and we just have to find it. For example, in the ladder problem, we could use the Pythagorean theorem. Other times we have to be a little bit more clever, but we can always do it. Once we have that, since we're interested in the rates of these things, we need to differentiate. And we'll have to differentiate implicitly because we're talking about with respect to time. Finally, we can plug in the values that we know in the problem and solve for the unknown. Be very careful not to plug things in before you take the derivative, because otherwise that'll change what your derivative is and it's not right anymore. So always, always, always make sure to take the derivative first. Okay, so with these 5 steps, I think we're ready to look at an example. So let's head over here. Our first example is about filling a cone with water. So we're filling this cone with water. The water is flowing in at a rate of 5 cubic meters per minute. We know that the cone has a radius of 1 meter and a height of 3 meters. The question we're trying to answer is, at what rate is the height of the water changing when that height of water is at 1 meter? Okay, so the first step is to draw a picture, which I've already done for us. Now we want to label what we know, step 2. Well, what do we know? We have the rate that the water is flowing in at, which for us we want to think about that as the derivative of volume with respect to time, because that's going to be how much of the volume of water is changing. We also know the cone has radius 1 meter and height 3 meters. And we're looking for the rate of the change of heights when the height is at 1 meter. In our problem then, this is the 5 cubic meters per minute. Our radius of the cone up here is 1, so we'll call that r equals 1. The total height of the cone is 3 meters. And we're interested in the height of the water, which I'll call a little h, when that height is equal to 1. As I mentioned, we're looking for the rate at which the height of the water is changing, so the question we're trying to answer is, what is dH dt? Okay. Now, our next step is to write an equation relating the things we're interested in. So the things that we want to know about are volume and height. Well, this is one of those situations where there's already a ready-made equation for us, because we know the equation for the volume of a cone. And that's given to us by volume equals 1/3 times pi times the radius of the cone squared times the height. Unfortunately, we've got too many variables there right now. We only want to know about volume and height, so we need to figure out a way to get the radius out of this equation. We can do that because we know a couple of other things about this cone. So, the goal right now is to write an equation relating radius and height so that we can substitute back into this equation. What do we know about how the radius is related to the height? Well, we know the total height of the cone, we know the radius of the cone, and that is going to be related to the height of the water and the radius of the water, because those are similar triangles. Now, for similar triangles, what we like to do is to say that 3 to 1 is going to have to equal h to r. Now we can do a little bit of algebra, and we'll multiply r over to the other side, and then we'll divide 3 over to the other side because we want r by itself. We'll get r equals 1/3 h. Awesome. Now we can plug this equation back into the volume equation up here. Then we'll get volume equals 1/3 pi times the quantity 1/3 h squared times h. The first thing we'll want to do is to square both terms inside the parentheses, and then we'll combine our like terms. We'll get volume equals, now 1/3 squared is going to be 1/9, and I'll multiply it by the 1/3 so that we get 1/27. We still have pi. And then we'll have h squared times h. So now we'll have h cubed. Now, the question we're trying to answer is the rate at which the height is changing. So we go to step 4. Now we're ready to differentiate implicitly. We want to take the derivative of both sides of the equation, and we'll get, I'm going to move down here, we'll get dv dt is equal to the derivative of this side. Now, 1/27 and pi are constants, so we'll just hang on to those. 1/27 times pi. And now we want the derivative of h cubed with respect to time. So we take the derivative like usual, we'll get 3h, but since h is a function of time, then we also have to multiply by dh dt. Wonderful. We're almost there. Now we're ready to plug in what we know and then solve for the unknown. So what do we know? We know that dv dt is my 5 cubic meters per minute. I know that h is at 1 at the moment that I'm looking for. So then we get 5 equals 1/27 times pi time, oh, I'm sorry, I made a mistake. The derivative up here should be 3h squared, not just 3h. There we go. That's a little better. But we still take 1 and square it, so that's not going to change anything. But we still have our 3, so I'm going to move that 3 up to my fraction over here. And then we've got dh dt. Okay. Now we want dh dt by itself, so we're almost done. We'll just divide by our coefficient over to the other side, and we'll end up with, well, this becomes 1/9. We multiply by 9 over to the other side, divide by pi, we'll get 45 over pi equals dh dt. And that will be the rate at which the height of the water is changing when we have a height of 1 meter. So, we've just solved a related rates problem. Let's look at another example. Here, we're talking about the length of a shadow. So the story is that Steve is walking away from a 10-meter tall light at a rate of 0.5 meters per second. We know that Steve is 1.75 meters tall, and the question we're asking is, at what rate is the length of his shadow increasing? So, again, the first step is always to draw a picture. And I've drawn kind of a simple picture here. Here's our light. This is Steve. And then his shadow is going to be right here. So now we can move on to the next step, which is to label what we want. We know that the height of the light is going to be 10 meters. That's right here. So we'll label it as 10 meters. We know that Steve here is 1.75 meters tall, so we'll label that 1.75 meters. And we also want to know about the distance between Steve and the light. So we'll call that D. And we also want to know about his shadow, so we'll call that S. Now, that is everything the problem gave us, so we're ready for the next step, which is to write an equation relating the things we're interested in. Again, we have a set of similar triangles, so we can use the same trick that we used for the last problem. We know that 1.75 is to S, as 10 is to S plus D. Now, we could differentiate right away, but that would be a little bit messy. Let's do some algebra first. So we'll multiply this denominator over to the other side, and we'll multiply S over to the other side. We'll get 1.75 times the quantity, S plus D, and that's going to be equal to 10 times S. We can distribute the 1.75 through, and we get 1.75S plus 1.75D is going to equal 10S. And then let's just subtract that 1.75S over to the other side, so we have all of our variables together. Then we'll be left with 1.75D is equal to 8.25S. Awesome. Now that we have that equation, we're ready to differentiate implicitly to find the rates that we're looking for. So, the derivative of this side, the 1.75 is constant multiple, we just hang on to that. The derivative of d with respect to time is just dd dt. Now on the other side, again we hang on to the 8.25, and the derivative of s is ds dt. Good. Now we have our derivative, we're ready to plug in what we know. Well, we know that the one we're looking for is the rate at which the shadow is changing, so we're looking for ds dt. That means we should probably know dd dt. Well, we are told in the problem that Steve is walking away from the light at 0.5 meters per second. That means the rate at which his distance from the light is changing is 0.5 meters per second. In other words, dd dt is 0.5. Now we can plug in 1.75 times 0.5 equals 8.25 times ds dt. And finally, we just got a little bit of algebra to do. Multiply these together, divide over, and we'll get ds dt is equal to about 0.1 meters per second. So that's what related rates are all about. Just remember to follow those 5 steps. They'll help you out a lot. And now we can solve all sorts of wonderful problems that we couldn't before. Isn't calculus fun?